think we can start. Good morning, everyone, and welcome to the second part of this lecture on cosmology and geometry at the boundary, held by Paolo Benincasa from Instituto de Fisica Teorica de Madrid. I would like to ask you today if it's possible for you to turn on the camera, just to have a visual contact between the speaker and all the participants for the lecture, if it's okay. If you don't have the chance to do it, don't worry, it's okay. Paolo, the stage is yours.
Okay, thanks a lot. And okay, so in this second lecture, we will switch a little bit gear, and we'll start to describe a first principle formulation, mathematical formulation of an object, which will turn out to have all the properties we ascribe to the wave function of the universe. It's going to have contact with the last part of the lecture yesterday. And for this reason, before getting our hands dirty with a little bit of positive geometries and projective polytopes, I think it's a good idea to make a brief recap of some salient feature of the lecture of yesterday. So I think the main point of the lecture yesterday are that first, the wave function is a boundary object which lives on a space-like surface. So it has all the time evolution integrated out. And so the general question we are asking is how we can extract the fundamental physics just by looking at the wave function without making any explicit reference to an explicit time evolution. So without putting things happening by hand in the past. Second message is that indeed there are ways to compute the wave function just from boundary data. And the boundary data means, for example, we are working in momentum space, which means the spatial momenta which are on the boundary. And we saw that at least in the case of scalars, what really matters are in quotation mark the energies, so which really are modulus of spatial momenta. And we saw a specific way of doing this, which is a recursion relation, which has this schematic form. So actually, we saw another important point is that given an arbitrarily complicated theory, it's possible to write the wave function in such a way that the really the specific feature of a given cosmology can be all condensed in coefficients, and so we can define a universal integrand, and so we can study that object and try to extract as much information as possible from them. And this information will have a universal feature in the sense that it's going to be common at least to some large class of models. And for this object, we know that we discussed yesterday the existence of a recursion relation, which tells us that the wave function with the endpoint contribution to wave function times the sum of the total energies, which is this sum with the axis, is given by all the possible the sum of all the possible ways of cutting one edge of a graph. Let's see. And the price one pay that when you cut an edge, you have to shift the energies of the vertices which were the endpoints of that edge. So this will be x v plus y v is x v prime e plus y e plus, and then here we have the sum over all the sets of the edges. Okay, so one nice thing of this way of discussing the contribution to the wave function is that we, rather than writing down the full Feynman diagrams, we can map it in what I call the reduced graph. For example, again, the simplest example is this 4-point graph, which can be mapped into this reduced graph, and which is labeled by the energies, the sum of the energies entering at each vertex on the vertices, and then by the energy of the internal state here at which labels the internal edge. Okay. So, namely, in this specific case, x1, if this is state 1, state 2, state 3, state 4, x1 will be modulus of p1 plus modulus of p2, or if you want here, you can shift it also by the energies of the related to the coupling constant at that vertex. X2 is given by p3 plus p4 plus epsilon 2, and y12 will be modulus of p1 plus modulus of p2. Okay. So this is, and then this recursion relation tells you that without having to do to write explicitly down what the propagator is, all the integrals over over time, you can just compute it as sum of products of lower point amplitudes. In this case, will be just the product. In this specific case of this 4-point contribution, will be just the product of two 3-point wave function. Okay. Another important point is that we saw that this this recursion relation, the recursion relation has a combinatorial origin, or better, it has yeah, combinatorial origin, which means that they are really can be thought of a set of combinatorial rules, because you can implement them by dividing a graph in iteratively in connected subgraphs, which is equivalent to say that you have to cut one edge at a time. For example, again, just to make things clear with the example that the simple possible example. The algorithm was telling you that you have to divide this graph in all the possible subgraphs, which means that, for example, the first graph is this is the first subgraph of a graph is the graph itself, and to this you have to associate the inverse of the sum of the external energy to this graph. So it was x1 plus x2. Now you can divide this, you have to divide this in two connected subgraphs. There is just one way you can do it, which is taking the two vertices separately. And then you have now to associate the sum of external energy to each of these vertices. For example, in the case of the vertex that I rounded with the blue circle, the external energies are x1, which external energy for the full graph, plus also the internal, the energy of the internal state. Similarly for the other. And then in one shot, without making any reference to any time evolution, anything, you get the answer, which is free of spurious poles. All these are physical poles. And this is really what you study. This type of perturbation theory is not new. What is new is the combinatorial way of implementing it. And this is what you study typically in quantum mechanics, and some people call it old-fashioned perturbation theory. Now, there is an important point that I want to highlight here that I'm not sure that went through yesterday, which is there is a correspondence which between subgraph and singularities, which is to each subgraph correspond a singularity of the wave function. In fact, when one says that in order to write this formula, I have to associate the inverse of the sum of the energy which are external to the graph. Well, the inverse gives you a pole, so that's a natural singularity, a singularity of the object. And the fact that this perturbation theory concerned just with physical poles guarantees you that you can, given an arbitrary complicated graph, if you want to know where are the singularity of this graph, you have to look at the subgraph and to associate to it the inverse of the sum of the energies. For example, let me write some very complicated loop graph. And associate x1, x2, x3, x4, x5, x6, x7, and x8. And I will indicate the energies of the internal states as y, ij, where ij are related to the indices of the axes at the endpoints of the edge. For example, this edge will be y34, sorry. Okay, so for example, we want to know where are the singularities. If you want to know it without having to write down the full answer, we can say, okay, let's see what are all the possible subgraph. For example, if I take this guy, this is a possible subgraph. To this, one associate the inverse of x4 plus x5 plus x6 plus now all the energies related to the internal edge that this blob is cutting, which are what I call the energy which are still external and but are related to the propagator, which in this case are y34, then y48, and y67. So you know that this graph, which can be arbitrarily complicated, has a singularity there. And then if you want, for example, just to make a list of the possible singularity, which means that you have to make a list of all the possible graphs. Okay, so all the possible subgraphs related to a graph. And I think this is very important and will show up in what is going to be the core of the lecture of today. So I think this is the main point I wanted to highlight of the lecture of yesterday, but if there are questions both related to this or related to other point of the previous lecture, now it's a good moment to ask.
I have a question actually. So let's consider this example, for instance. So your results directly doesn't have anything to do with the loop, the integration over some loop variable, let's say. So this is directly the result in this case.
No, actually, in the case of loop graph, remember this object, this way of computing it provides all the time a meromorphic function. So in the case of a loop graph, what you get is the integrand, where not only now you have to do the integration over the energies associated to the coupling constant, but also you have to do also the integration over the loop moment. So in general, for that reason, is really appropriate to call what you're computing a wave function integrand. It's an integrand also at the tree level, but even more at loop level, because you still have to do the loop integration. However, just to make, given that you introduced this point, it's good to make a comment. Is that, for example, it's true that if you care about some loop contribution, you want the full answer. You want to integrate over the loop momenta. Nevertheless, and this is what we learned in the old literature in the recent years in amplitudes, you can think to study also to have a way to define an integrand and study several properties which are there and see how them transfer to an integral. So you can try to you can have the study of an integrand as intermediate steps to try to even understand what is the answer that you're supposed to get later when you want to integrate or you want to do the loop integration. And always it's nicer to work with the meromorphic function as much as you can before trying to deal with all the complication coming from transcendental function and all other more complicated function. Other questions? Okay, if not, let's move to the actual topic of this lecture. So, as I mentioned at the very beginning, I would like to construct an object which, in principle, shouldn't know anything about physics, but then we should discover that it has all the properties that we ascribe to a wave function. It should be a way to have a different first principle formulation of a function that we can study to extract more information that won't be obvious if we still keep working just on Feynman diagrams or other more standard techniques. Before doing that, let me do a brief point of interlude. Because I assume that not everyone might be familiar with some use of projective geometry, and so it's good to waste at least some minutes in making some point clear, because it's going to come all the time in the discussion. So for the next few minutes, it's going to be a little bit of math with no really any connection to physics, but bear with me for a few minutes. So when we talk about polytopes, you can think it in two ways. Either they are a convex hull of a set of vertices, yeah. So for example, you're given a set of vectors, say 3 vectors, and you have to take an interior with respect to these 3 vertices. In this case, there is just one possibility, which is this one. For example, if I have 4 places like this, you have a square. If I will have 4 places like this, you are taking the convex hull, so you will still have a triangle, and one of the points will be internal. There is a second way to think about this. And I'm making the simplest example, which is I can draw on a plane. However, you can generalize this to arbitrary dimensions. A second way to do it is that you can think of a polytope as defined as having a set of linear inequalities, and you have to take the overlap between in the space defined by these inequalities. For example, let's say that I have I have a space which is given by in the plane, which is given by coordinate s and t. I can take s greater or equal to 0, t greater or equal to 0, and 1 minus t minus s minus t greater or equal to 0. This will in the plane t and s t equals 0 will define this line. S equals 0 will define this line. So the positive, the fact that you are taking inequality means that you are taking, in the case of the s greater than 0, you're taking the upper plane, t equal to 0, the right plane, and then 1 minus s minus t define this other line. So the intersection of the part given by the inequalities is just this interior. Okay. So this is a standard way that you can find in any book which talks about polytopes, or and an important point now, which is less standard, is that given one of these objects, given a triangle in this case, you can always associate a differential form. So there exists a differential form, which I will indicate with omega, which is called canonical form. Which has the characteristic to have just logarithmic singularities. Okay, what does this mean? This means that, again, in my example of this triangle, the differential form that has just logarithmic singularity means that one can write it as some number, and then some we are in a two-dimensional space, so some d-log form. In any case, or said if you said in a different way, it has to have just if you will write explicitly in terms of the coordinates, which in the case are s and t. So, well, in this case, really, to be more explicit, okay. if you open it up to the log, what you want is that here you have a meromorphic function, and then here you write it as ds. Sorry, here it was correct before. Okay. So, and this omega, which is called, with this big omega, which is called a canonical function, we have just, it will be a meromorphic function. Now, another feature is that this, the poles, a meromorphic function with just simple poles. Now, another important feature is that in the simple poles should reflect the boundaries of the polytope. The boundaries are, in the case, the sides of the triangle. For example, given that, as I said before, this boundary is identified by the equation t equals 0. This other boundary by the equation s equals 0. This other one by 1 minus s minus t equals 0. You want this meromorphic function should have singularity just in these three points. So one will have st, 1 minus s minus t, ds dt. Okay. So this uniquely characterizes the polytope, which means that if I don't tell you anything, I tell you that there is a space in which you live in this case will be P2, and I give you, I don't this information, which is the canonical form, you can immediately associate uniquely a polytope. Now, written this way, it's written in a way that the fact that we are in projective space is not that manifest. But the way that you can think about it is that, for example, I can introduce a third coordinate. You see that all these polynomials are not homogeneous. This guy has here a 1. To be in projective space means that all your vectors they form a class of equivalence, which is given by a rescaling. Okay. So to do that, you have to rewrite your inequalities in terms of homogeneous polynomial. In this case, homogeneous linear polynomial. So I can introduce a third coordinate, which is called u. I can write this in this way. And here I have to divide to the fact that I have this rescaling. So really, you so you have a space which I will call big Y, which has coordinate s, t, and u. So your vectors are in principle vectors in R3, but then you kill one of the degrees of freedom because you are taking rays. So all the points on a given race starting from the origin of R3 are equivalent to each other. And so, for example, the saying that, like in this case, will correspond to have u equal 1 is just a specific choice of a patch. All this expression can be written in a projectively manifest way.
Sorry, Paolo.
Yes.
Just a stupid question. S and T are complex valued.
No, in principle, you take them to be real, because if they are complex, you cannot define what is greater than you cannot really define inequalities.
Okay.
Then, when you study it, when you want to talk about, once you have in principle, when you talk about these polytopes that you can want to define them in terms of inequalities, they are defined on over a space which is real. However, once you have your function, you can always, you're allowed to make analytic continuation and then consider these coordinates as complex. Okay. But for constructing themselves, you have to think about them as real.
Okay.
And so, in a more projective way, I say that you can think of it to be in a space given by the coordinate S, T, and U, which these are in P2. And then, given that we said that this plane S equal 0 is a boundary, you can a plane is identified, uniquely identified by 2 points. So, for example, if I take this vertex, I call it 1, this vertex, I call it 2, this vertex, I call it 3. If I take a vector x1, which give me the coordinates of this vertex, x2 the same, so these are the vectors of the 3 vertices, then s equals 0, which is given by this side, is uniquely identified by a plane given by 1 and 2, the vectors 1 and 2. And therefore, this plane can be written as x, this is the Levi-Civita symbol. And hence, I can write and the same for the other one. So I can write my differential form as y1, 2. Now it's fragmentation, y2, 3, y3, 1. Now here I have to put a numerator, and here, where this notation means simply that I'm contracting through a Levi-Civita symbol the vector y, which is the vectors of my coordinates, x1j and xk, x1 1 and x2 x1j and x2 2k. So when you say that s equals 0, you are saying that this brackets has to be equal 0. And this object is the same. This angle bracket are contraction among the vectors through a Levi-Civita symbol. Now we need to fix the numerator. In order to fix the numerator, we are in projective space. So it means that all the vectors rescaled by which we differ by a rescaling are equivalent to each other, which means that you want your differential form to be unique, that is invariant if you rescale any of the vectors. So the numerators should be such a way that this property is satisfied. You notice that for y, you have 3 y's in the denominator, 3 y's given by the measure. And so for y's that is satisfied, we need something which satisfies this property for these are the vectors which gives you the vertices. And this is simply given by contracting 1, 2, and 3 and squared. And so, and this it's this very same object, but written in a completely manifest projective way. Okay. A last comment is that given a geometrical figure, a polytope, you can always define a dual, which is just defined by mapping all the vertices in planes and planes into vertices. Now, which means that this originally was a plane identified by 1, 2, and gives you a vector. Let me call it Z3. Sorry, Z3. I. Now, in the dual space, this vector doesn't identify anymore a plane, but identify a vertex. So we have a set of three vectors, I3, J3, Z2, and Z1, which are defined in this way, which gives you vertices of a new polytope, which in this case are still three and is still a triangle. So in terms of the Z, which are the vertices of the dual polytope, this differential form, which is associated to the original polytope, can be written as y1, y2, y3, where this, let me erase this, where this round brackets means just the simple contraction between y and z. Okay, here the measure is still the same, and here for projectivity we have just 1, 2, 3, where now this 1, 2, 3 are not this one, but rather are these z's. Okay, okay, just for yeah, okay. And why I want to write this the canonical function in terms of the vertices of the dual polytope? Because one thing that you see in terms of geometrical interpretation is that when you write omega as y1, y2, y3, 1, 2, 3. This 1 over this term, the canonical function, is nothing but the volume of the dual polytope. So, and to see it, you can think about the formula to compute the area of the triangle in this case, which is given by the determinant of the vertices. So this object is what we will obtain by just thinking about the area in the term. So just to summarize, the important points is that one, polytopes are uniquely identified by their canonical form. Two, which actually I didn't say, but it's important to say, an important feature of this canonical form is that if I take a residue of any of the singularities, let's say 1, y2 equals 0 of the canonical form, the result is still a canonical form, omega prime, which lives in a space with one dimension less. In fact, if you think about it, in this example of the triangle, if I take for example, the residue for S equals 0, S equals 0 is identifies for the triangle this side. And you obtain a differential form, which is still, you still have a differential form, which is given by this. And in projective terms, this is exactly identifies for you this segment. T equals 0 is here and T equals 1 is here. So and these denominators identify still the boundaries of the polytope of this in this case of this segment. So the important point is that the differential form is associated, given a polytope, to it is associated, you have a differential form. Polytope has boundaries which are still other lower dimensional polytopes. So when you take the residues of this canonical form, you get another canonical form which is uniquely connected to the polytope related to the boundaries of the original polytope. Okay. Question at this point, because it's I think it's a lot of information in a very quick way, so it's important that this point is clear, because all the rest is going to be based on this.
So the procedure of considering the residue is just a projection of your polytope on some subspace.
Well, if you like, a modern projection is just taking your polytope, taking a hyperplane of one dimension less, and making the intersection. And what is the result of that? If, in this case, for example, when you're taking an hyperplane which corresponds to a boundary, which means that it, for example, here I'm taking in this specific case of the triangle, I'm taking the intersection of the triangle, of my triangle with this this plane, and then this is what is left over. In principle, you can think if I will start to go crazy and just randomly choose planes, I can still consider, for example, intersection of my triangle for this plane, but this is not a boundary. In fact, it's not going to be reflected in the singularities of the polytope. So, in a sense, the singularities of the canonical form identify some special planes which intersected by with the polytope gives you its boundaries.
And can you say something about the canonical form of not the dual polytope, but the original polytope? Is it related to the volume of the polytope, or this feature is just for the dual polytope?
So, if you like, you know, what's dual or not, it's a term of definition. So even the dual polytope has a canonical form. So if I take the canonical form of the dual polytope, the coefficient of that form is the it's the volume of the original polytope. So say so let's say I have a polytope P. I have a differential form which has a coefficient with some measure. This is in Pn, and to this I can always associate a P tilde, and in this case omega is the volume of P tilde. However, also P tilde has a differential form, which let me call omega tilde, which I can write it again in this fashion. And then omega tilde is the volume of P. Okay, so the reason for which it's convenient to think about in terms of differential form and of the canonical form is exactly because of the correspondence between boundaries and singularities of the omega. And going ahead, making a connection to physics, the general claim is that the wave function of the universe is given by the coefficient of the polytope constructed in a certain way. Now, what I will explain now, it's a way to construct a class of polytopes which was unknown in the math literature before, which has this feature. Okay, and given that as I'm trying to stress now, this differential form has just singularities, and the singularities correspond to boundary. This means that the residue, the singularity of the wave function are related to the boundaries of the polytope we will define, and the residues of the wave function is going to be encoded into the canonical form associated to the polytope, which is on the specific boundary one choose. Okay, so this is to start to make clear why I'm saying all this, and in order that it doesn't stay as just some math talking. Other questions? Because I think this is a good point to ask many questions about this, because what I'm saying now is general, and I can reference. I think it's in the list of references I give you, but you can find 2 references on the subject. One is Arkani Hamed et al, and it's called Positive Geometries and Canonical Form. And then there is another one by myself and Matteo Parisi, which is from, okay, let's see if I can give you the archive number, which is 2005. So the subject is kind of fresh, even if polytopes have been known since long time. There is their study in terms of this differential form is kind of recent.
Can I ask? I mean, a question.
Sure.
Just maybe a bit technical, but I mean, maybe a bit stupid, but this numerator, when we take the residue, this numerator with the y, dy, so do we?
No, it's a measure. This, if you write it explicitly, this you're talking about this, right?
Yeah.
This will be just given by, for example, if I have some space with coordinate x1, blah, 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 x n plus 1, then here, this is going to be just given by the wedge product of j from 1 to n plus 1 of this dxj, all divided by the volume of GL1, where this volume of GL1 takes into account the fact that given a vector, because this in principle looks like a vector in Rn plus 1, but really, as I said before, we are in projective space. So the vectors which differ by rescaling are all equivalent to each other. And so this takes into account the fact that you have 1 degree of freedom less given by this equivalence class. So this is really the measure of your space. For this reason, it's a differential form. It has, and that's the measure. Given that to talk about numerator, let me make a point about this, which I think it's good to make now, even if I'm not 100% sure that I would reach to use it later on. Now, let's say that we have a quadrilateral. Now, in projective space, points meet always at infinity. So there is no, so if, I can draw my quadrilateral, let's say, let me draw it like this. Okay, so in this case, the differential form will be given by the, let me call this y, 2, 3, and 4. Will still be given by plane identified by these vertices. And now here I have some numerator, and I have my measure. Now, contrary to what's happening with triangle, when I consider if this is invariant under rescaling, you see that already is not invariant under the scaling of y, which means because I have 4 y's in the denominator and 3 y's in the numerator in the measure, which means that n should be really a function y, is no longer just a constant given by the vertices of the triangle. The way that you identify this guy is that obviously you need here some sort of polynomial which contains zeros of the differential form. And there is a nice geometric way to identify this. Ny equals 0. It's a polynomial which identifies the zero of the differential form. There is a nice way geometrical way to figure out what this numerator is, which is given by, okay, let me rewrite my quadrilateral here. Sorry. So here the vertices are given by where the plane identifying the boundaries intersect. But this intersect, and then you take all the interior. Okay. However, they also intersect outside the polytope. I can prolong this and intersect here. I can prolong this and this intersect here. They also define a plane, and I won't give you the proof, but this plane, it's so the intersection of the planes, the intersection, let's say the points given by the intersection of the planes outside the polytope identify another hyperplane, and this is the plane which gives you the numerator, where this differential form intersect. Okay, so if you have these vertices 1, 2, 3, and 4, you can have, for example, what I want to say. So you can write it as y 1, 2, which intersect 3, 4. Okay. In any case, this is just to make clear that there is a generic way in which you can construct arbitrary polytope, and even a numerator, which is not trivial as in the case of the triangle, has a specific meaning, which is given by the zero which is given by the intersection of the boundaries of the polytope outside of the polytope. Just this is for completeness. Now. Let's go now back to cosmology and to the construction which will allow us to study the wave function. Okay, so this object that I will introduce now, we dub them cosmological polytopes for the reason that they are associated with wave function of the universe. To make clear what's the connection with physics and about the construction that I'm going to explain in physics, let's start from our graphs. So let's take this simple graph, and we say that it has to the vertices we associate some labels x1, x2, and actually let me write them now, x1 and x1 prime, and to the internal edge a label which is y. In physically, these are the x's are the sum of the energies of the external states at a vertex, and the y is the energy of the internal state. Now, if I take this graph, I can define a space which I call big Y, which is given by the set of energies x1, y1, x1 prime. So these are vectors in R3 that then you have to project them out. Now to define the equivalence class to be in projective space. So this is in principle is P2. Now I can define some vertices which I will call them x1 given by 1, 0, 0, which is a basis for R3 for P2, x1 prime 0, 0, 1, and y1 0, 1, 0. And now there is a unique correspondence between this graph and a triangle whose midpoints are identified by these three vectors. So I have here a triangle. This point is identified by x1. This other point is identified by x1 prime. This other point is identified by y1. Which means that if I want to talk about in terms of the vertices, this vertex is given by x1 minus 1 plus x1 prime. And this you can find it just by asking this three, the x1, x1 prime, and y to be the midpoints between the vertices. Okay. Now, as I said before, to this, and so if you like the vertices, I can call them Z1. This is given by, for example, if this is Z1, is 1 minus 1, 1. Z2 is, which is this one, is 1, 1 minus 1, and Z3 is minus 1, 1, 1. For everything I said earlier, to this triangle, you can identify, you can associate a differential form, which is given by the planes identified by all these vertices, Z1, Z2, and Z3, which, write it in a very generic fashion, where, if you remember, these angular brackets are just contraction of these vectors through a Levy symbol. Now, just to make confidence that I'm doing something physical, if you were to explicitly compute these determinants, because at the end of the day they are determinants, these angular brackets, you will obtain x1 plus x2, x1 plus x1 prime, x1 plus 1, y1, y1 plus x2. With here the x1, the x1 prime, the y1, and obviously the volume of GL1. So the point is that you start to see here that the canonical form of this triangle contains the wave function associated to the graph with the two vertices. Actually, so is this clear? And this correspondence, it's unique. Okay, so substantially the energies gives you a well-defined space with well-defined coordinates, because that's they act as local coordinates. You can define, let's say, the vertices and sides of the triangle gives you of the graph gives you a basis for this space. This basis gives you a midpoint of a triangle, define uniquely triangle through their midpoints. And then already here, you know that as in any polytope, one associated a differential form, and the coefficient is given by the wave function. Now, let's say that I have two of these segments. Two of these graphs, sorry, x1 prime, y1, x2 prime, y2. So to each of them, actually I can define a space y, which is given by all the coordinates of both of them. To each of them, I can identify a triangle. Now with here labels x1, x2, x1 prime, and y1, here x2 prime, and y2. So in a sense, they are different graphs. They live in the space, and now this is in P5. And there are two triangles, so we don't talk to each other. Now, we get to the convenience of using this reduced graph. If I can think that I can take these two graphs and merge them, for example, in a vertex, for example, identifying x1 prime with the x2 prime, for example. Let me call this just x prime. If I do this, that, I obtain this graph. This y1, y2. Or also, I can identify both the vertices of one graph with the vertices of the other graph. So x1 prime equal x2 prime, and I'll call it x prime, and x1 equal x2, and call it x. And one obtain a loop graph. And then here's y1 and y2. Now, this also corresponds to doing something with this triangle. For example, if I ask the x1 prime, x2 prime are the same point, I'm projecting on a subspace on one dimension less, where these 2 points are identified, which in other words means that I can imagine to intersect these two triangles in these vertices. Sorry. Okay. So if I intersect in that vertex, I obtain something, it's one dimension less, so it lives in P4. And you get a figure which looks like this. Now I'm drawing these dashed lines because in principle this should go in a fourth dimension, and it already is difficult to draw something which is 3 dimensional. Something that's 4 dimensional is even more difficult. And if you take the convex hull of this object, you get some sort of double pyramid. So let me draw it better separately. And to this also, now there is another canonical form, which has the same structure. In the denominator, you have all the boundaries, and then you have some specific numerator. Now here instead, you are projecting on you are intersecting triangles into point. So what you get is an object which is supposed to live in P3. Sorry. This belongs to P3, and you can imagine to be something like this. This is x prime. And if you draw the convex hull, it should be something like this. A sort of truncated pyramid. And again, now, here comes an important point. Remember, in the recap I made of the previous lecture, I wanted to stress that there is a correspondence between subgraphs and singularities of the wave function, which means that there is a correspondence, given that the singularity of the wave function gives you the equation that identifies the boundaries of the polytope, means that there is a correspondence between the boundaries of the polytope and the subgraph. So if you want to know what are the boundaries of a polytope, again, you have to list, you can use the graph and you can list all of them by taking all the possible subgraph. A second important point to make is that, you know, now I'm drawing triangles, I drew something in P3, it's still doable. Already, there is some difficulty in drawing an object which is in P4. And one thing that you can see already is that the space where this object lives is substantially the space of energies. And bigger is the graph, bigger is the space of energies. So I won't be able to draw anymore any polytope. So how I'm supposed to study them? The point is exactly this correspondence with the graph. You know that for how much a polytope is complicated, there is a graph associated to it. So you can study the graph and you can study all the properties of the polytope through the graph. So you can think to associate to the graph all the combinatorial feature that a polytope has. And so if one wants to keep track of the structure of the polytope, one needs to be able to associate boundaries and vertices to the graphs. For example, if I have, so what we can come up with is that if I have this simple graph, which is let's say our building block, which is associated to the other building block, which is the triangle. The triangle has vertices x1 minus y1 plus x1 prime, x1 plus y1 minus x1 prime, minus x1 plus y1 plus x1 prime. Now, one can make marking on the graph which correspond to the vertices. For example, if I take this vertex, which is given by the sum of the x's and minus the y, I will I will represent on the graph this vertex through a marking given by an open circle in the middle. If I want to represent this vertex, which is given by the sum of x and y minus x prime, so there is the sum of x1 and y prime, I will make another marking close to the vertex labeled by x1, and similarly for this other vertex will be given by marking here. So which means so I know that given an arbitrary complicated graph, so x1, x2, x3, x4, x5, x6, and x7. The associated polytope have a set of vertices given by this structure, which is sum and differences of x's and y. But I know that, for example, if I take just this segment, I have x1 minus y1. Oh, okay, let me write this: y12, y23, and so on. y23 plus x2, x1 plus y12 minus x2 minus x1 plus y12 plus x2. So to each of this of this segment of this subgraph, you know that there are these three type of vertices related, and so you can make the list of all of them related to this to these 2-point subgraphs. So to continue the list, then this one will contain the graphs x2 plus y23 minus minus y23 plus x3, x2 plus y23 minus x3, minus x2 plus y23 plus x3, and so on. And you continue the list, and you know that these are all the vertices associated to the polytope. Okay. And so now, what's important here? We know that we have a differential form, which is given by a coefficient and our measure. Now, I also know that all the singularities are associated to the boundaries, and I know that the boundaries are associated to subgraphs of the polytope. So when I take the residue of one of these singularities, I obtain an object which lives in one dimension less, because when you take a residue, are imposing one condition. For example, just to make things clear, let's go back to this guy. We know, just because it's very easy to write the final formula, we know that explicitly this is the differential form associated to it. Sorry. Now, let's say that I want to take the residue of, let's say, the residue of omega with respect x1 plus x2 equals 0. Okay. Now, we know that this is associated to taking the subgraph, which is the graph itself. And it's gonna give you some omega prime, which is given, for example, by 1 over y1 minus xy squared. And here I have dx1, dy1, volume of GL1. Now, in terms of, so how can I see which vertices of the polytope survive? Now, there is a graphical way that we can do it, and that if you were to make an intersection between the polytope and the plane which defined by x1 plus x1 prime equals 0, you will see that the only vertices which survives are these two. This is an exercise you can do. So you have to ask, given a polytope which has these vertices, I intersected with a plane given by this expression, and which are the vertices which are on this plane. And you will discover that are these two which do not contain a combination which is a sum of the x's, which means that it does not contain this green open circle. So I know that when I take the subgraph which include an edge inside, the vertex label in the middle is not there. So I can either indicate it like this or saying that there are just these two vertices which survive. Okay. Now, I'm doing this correspondence directly with this formula just to make things clear about what's happened on a functional level. But this is really useful when, for example, you don't know the final formula and maybe you don't want to write down, but you want to study directly properties of what's happened on the boundary. And why you want to do that? Because again, one thing that we learn, especially in the literature in the scattering amplitude, is that the physics is really encoded in the residues of the scattering amplitudes. And here is the same. In fact, for example, in this specific case, saying that I'm looking at x1 at the residue of the wave function for x1 plus x1 prime equals 0, I'm saying that I'm looking at a configuration in kinematic space where I restore conservation energy, and so I should get all the physics associated to flat space. Okay, so going back to this more complicated graph, so there is a general way in which you can figure out which vertex of the polytopes are in on a boundary or not, which is x1, x2, x3, x4, x5, x6, x7, which is one, consider a subgraph G of, this is my graph, big G. So erase all the vertices associated to the middle of the edges, which are inside of G. 3, erase all the vertices external to G, but which are close to its most outer vertices. Sorry, let me call the vertices of the okay, to the most outer vertices of G. Example, let's say that I take this subgraph. The vertices which are not there will be the ones associated to this and this, which satisfy the condition 2, and then also the vertices associated to this, and this, which are the ones from this condition. Okay, so I could write, a positive way of writing the vertices which are there rather than writing the vertices which are not there. Okay, for example, I can say that again for this subgraph, the vertices which are there are the one related to this marking, the one related to this marking, and then this is in the middle. And then here I have all 3 of them. Here I have just 2. Okay. Why this it's important? Again, for example, one thing we were able to do by using this this labeling. So first of all, in this way, you know all the vertex structure of all the possible graphs, because, for example, you can start to you have you know the structure of the vertex of all the possible boundaries of the polytope. Again, the boundaries of the polytopes encode information about what are the residues of the wave function. Now, using this marking, we were able to show to make a new proof of the cutting rules for the scattering amplitudes by just focusing on the boundary which is associated to the amplitude and see what is the vertex structure there. So the point of doing this is that you can figure out that there is a lot of information of the wave function, which are simply a consequence of the way that these polytopes are constructed. Okay, so question at this point, now we'll start to make some other example to make all the statements clearer, but it's important that you make some question, because I understand that this is very simple, but one needs to swallow it a little, to digest it a little bit. Okay. Sorry. I'll just, okay. I realize that I have a maximum number of black words, white words I can use. Okay. So now let's make all this business a little bit clearer. Let's say that so what I want to show you now is the fact that how unitarity emerges, flat space unitarity emerges from this cosmological context. Actually, sorry, before doing this, let me make a last remark, which is the following. Now, let's say that I have this graph. X1, X2, X3, Y1, 2, Y2, 3. We know that it has a polytope which has the following vertices: X1 plus Y12, minus Y12 plus X2, X1 plus Y12 minus X2, minus X1 plus Y12 plus X2, and then X2 minus Y23 plus X3, X2 plus Y23 minus X3, minus X2 plus Y23 plus X3, which again are the vertices which will be related to the triangle associated to the two subsegments. Because if you think about it, when you take these triangles and you intersect them, the number of vertices doesn't change. If you start with two triangles, so you start with 6 vertices and you intersect them in the middle, the result is going to still have 6 vertices, and which are the same that you have before, but projected in the subspace. Now, let's say that I want to study the structure of what will be the wave function associated to this object. Okay, And let's say that I'm interested in studying one by one all the residues of the singularities. So first of all, I know that one residue is given by is associated to x1 plus x2 plus x3 equals 0. Okay. And I expect, because this is the sum to the energy, to be the flat space amplitude. Okay. Now, so according to the rules I mentioned before, from the perspective of the polytope, you have an additional polytope, which we have a lower dimensional polytope, which is given by all the vertices but the ones in the middle. Okay, so but this one and this one. So you know that these four vertices should encode the flat space, this flat space amplitude for you. And in fact, the point is that if you compute the canonical function using this for vertices, now this object lives in a space which is given by x1 plus x2 plus x3, y12, y3. So this is in P4. When I take the residue, I go to a space y prime, which is now in P3. I have four vertices. It means for vertices which are linearly independent on each other. So I know that what is the result has to be a simplex. Sorry. For vertices which are linearly independent in P3 gives you a simplex. Which means that the canonical form you expect it to have a 1 in the you have here some denominator, a 1 in the numerator, and here you have if you compute it, what's the singularities related to identified by these four vertices, you will discover that the denominator, that this guy, sorry, is nothing but y12 square x1 square y3 square minus x3 square, where I erased x2 and here x1, sorry, okay, here let me say just the x1, the y2, the y3, the x3. Okay. Now let's think of some more general argument how flat space how should I see flat space encoded there. Now, in order to do this, let's take some arbitrary complicated graph. And let's take this subgraph. So my polytope doesn't have these vertices. Now, one thing that characterizes the flat space is the fact that if you take the residue of a pole of the scattering amplitude, it has to factorize in the product of two amplitudes. So you have the optical theorem. So this is a consequence of a unitarity. So What does it mean that I take from this perspective a residue of a pole of the amplitude? This means that I'm focusing on another subgraph. So on this subgraph, I take another subgraph G, small g, and again I apply the rule that I have to erase a number of vertices. So I know to this boundary, the vertices associated, the vertices associated to it are given by all the vertices I have here, except I have to erase this one, and this one. This guy I don't have to erase it because they are already erased. Now, if you remember from the example I made before, when I took the, let's say, scattering amplitude here, erasing this two, you can see that writing this in a positive way. So these are the vertices which are there. A feature of a scattering amplitude is that in this language it is represented by a polytope given by the vertices which are close to the vertices of the graph. Okay, now let's look at what I draw there, but in this positive language. So rather than marking the vertices which are not there, marking the vertices which are there. So again, here from this blob, I have this guy, this guy, this guy, and this guy. Then here I have this one, this one. Actually, this one and this one. And then I have as last ones, I have this one, and this one. Notice now, this has the structure, this very same structure. So it looks like an amplitude. And indeed it is, because here, if this taking the red, this red blob is telling you that I'm taking the sum of all the x's and going to 0. Taking the blue blob is telling me that I'm taking the sum of this of the x's associated with the vertices of G plus the energies related to these external lines equal 0. So I have let me label x1, x2, x3. So I have x1 plus x2 plus x3, and then these other y's, I don't know, y34, y16, and y23, plus this sum of y equals 0. Okay, so if I'm imposing the energy conservation on a lower process, that means that it's becoming an amplitude for the argument I told you before. And this reflects in the language of how these vertices are organized by the fact that the polytope associated to it is defined by just the vertices close to the vertices of the subgraph. You can see that here you have the very same structure. So this marking that I drew in green also define an amplitude. While one thing that you can show, and that the yellow ones form just a simplex, and if you write the canonical form for this object, you will have the canonical function this phase. So where you're intersecting G with G, with small g, you have that you get the canonical form for G. If I call this other subgraph G prime times the canonical form for G prime times a canonical form for the simplex that I call sigma. And if you write all this explicitly, you will get the amplitude related to the subgraph G times the amplitude related to the subgraph G prime times here the canonical form for the simplex is just given by the product of the energies of the edge which are cut, which are like these edges. So this gives you a completely combinatorial proof of the fact that you need to have unitarity in a flat space. Why this is a proof, a different proof? Because we started from a situation which is completely cosmological. You have this polytope which are uniquely related to the wave function. Then we start to study what, and the polytope, okay, has a mathematical definition which in principle doesn't know about anything. And the structure of its vertices and or the boundary or the vertices which describe the faces of this polytope are inherited of how the polytope is constructed, which means that it's a consequence of how of the fact that the polytope is constructed by intersecting these triangles. And so this is telling me that when I look at a specific boundary which coincide to the singularity of the total energy is going to 0. And when I look at the vertex structure there, I see directly that the canonical function factorized. So really this polytope is given by a product of smaller polytope which correspond to amplitudes and this this part here, which let me write it more clearly. Which this is the canonical form of the simplex. This is the measure of the Lorentz invariant phase space. Okay, because it's 1 over the energies. Is what you will have if you explicitly write your Feynman graph in terms of in an explicit way. When you take the residues, you all the time get this 1 over the energies with respect to the cut edges. So I think this is important because in general you can ask more general questions about, for example, what means the other boundaries. So here I focus on the amplitude just because it's something that more or less people are familiar with. You know what you're supposed to obtain, and but this doesn't really depend on the fact that I know the answer. It's really the fact that you have this property. It's an inherited feature of how the polytope is constructed. Okay. I think, I mean, for my experience, these are things that needs to be a little bit digested. But the message that I want that you can bring back home is the fact that this construction really has provides a different way of a first principle definition, really, of what's the function, the wave function, at least for a general class of models. And any question that you can ask about what's the content, the physical content of the wave function, you can ask it to the polytope, like it was a kind of a sort of oracle. For example, if you have some let's say if you have a square, a way that you can consider a square, for example, it's like a combination of two triangles. So this means that you can triangulate, for example, you can triangulate a square in these two ways, for example. Now, when you have a cosmological polytope, so if you have cosmological P, the canonical form gives you, in principle, directly what is the wave function. That doesn't give you a specific representation. However, given that a polytope, it's if you like a generalization of any polygon to arbitrary dimension, you also can think of triangulating it. So there is a correspondence between triangulation of the polytope and representation of the wave function. And if you think about it, for example, let's go to this example, which is the simplest, not trivial one. When we use that recursion relation that I introduced yesterday, you can write this polytope as, if you remember, you write it in sum of two terms, because you have to, when you apply this algorithm, you have to iteratively cut the edges one at a time. So here you have two ways so you can cut the edges. So writing directly the answer, one thing you get is this is the total energy. Okay, let me write directly in a nice way the full answer. Times x1 plus x2 plus y3 plus. Okay. Now, again, as I try to stress, these denominators are all related to the subgraphs. The subgraphs are related to the boundary of the polytopes. These give you the boundary of the polytopes. But the fact that you write it in this way, like a sum, I didn't write, you can put the two terms together and having an object which is a denominator and a numerator. But if you write it like this, you, from the point of view of the polytope, you mean that you are triangulating it, because you are writing it in terms of two terms whose canonical function has a 1 in the numerator, which means that it is a simplex. Okay, so this old-fashioned perturbation theory corresponds to a specific triangulation of the related polytope, which means that if I give you a polytope and you know what is structure, you can, depending on what you want to know about the wave function, you can think to look at different type of triangulation of the polytope, and all of them obviously give you the same final wave function. However, for example, this one manifestly has the all physical poles, and it has this very nice feature. If you there is another triangulation which will give you the Feynman representation, which has spurious poles, and etc. And then there are others representation, because the number of triangulation are not 2 in general. If you take an arbitrarily complicated object, you can triangulate it in many ways, and then also you can get to representation that in principle don't have another way to get defined. This is one point. A second point is that for example, you want to ask about the symmetries of the function. This gets translated in what are the symmetries of the polytope. And more importantly, again, as I stressed before, physics is really contained in the residues, or in any case in the coefficients of the singularity of our observables. And this is automatically translating and asking any question you want on the boundaries of this polytope. And that rules with the markings that I tried to explain before, it's a very convenient way. I mean, I understand that for the first time that you see it is very, one has to digest it to understand it a little bit more detail, but probably from the way that I was doing it, you can see that at some point it becomes a matter of drawing and erasing vertices, and so the problem is completely simplified, and it has an intrinsic origin in the way that the polytope are constructed via this intersection of triangles. And what I try to show, to show you, where was it? Here is the fact that one thing that I can prove you in a few minutes is the fact that you need to have unitarity in flat space. And for example, I can make an analogous proof in the fact that you need to have Lorentz, even here you have already some suggestion. You need to have Lorentz invariance when you take a specific limit, so which corresponds to flat space limit, and this simply emerge from the way that polytope is constructed, because this intersection of triangles in principle don't know anything about all this business. And in this sense, one can say without making any overclaim that you can see really Lorentz invariance and unitarity emerging in flat space, emerging from cosmology. And this is very important, because what we are really after is to understand how even things we know, which when we think in flat space, they are fundamental up to some point, because you know, really fundamental physics goes to cosmology. It's encoded in cosmology, where we have access at higher energy processes. So you really want to know how anything that we can see come from higher energy. Because when we talk fundamental physics, what we are talking about? We are talking about what is the highest energy possible that we can access. And now the question are, for example, how you can see time of the actual cosmological time of evolution encoded, for example, in this polytope. For example, I know in the same way that I show you factorizations for the amplitude, I can show you factorization for the full wave function. The difference is, given that time is integrated out, in principle, there is not a clear connection to the fact that that is associated to time evolution. So there is a little bit more to do. Another question is about, because it's one of the fundamental principles we know that needs to hold, it's causality. And also that, for example, there are relations which are called Steiner relations in amplitudes. We prove that they do exist also for the wave function. However, while in the case of amplitudes, we know that there is a correspondence between having causality and having this time relation satisfied. In the case of cosmology, now we know that there are time relations, but still we are missing the link with causality, and because all the difficulties come from the fact that from the role played by time evolution, from the fact that it's in the object in the wave function is completely integrated out. And if you want to have some first principles, you cannot go in the bulk, make stuff, and then try to get. I mean, you can do it as check for models that you know that are causally unitary, but that won't be a general proof. So all this program, it's at the very beginning, and I hope I could convey you about some both, if you like, philosophical points that we are trying to make, and also some technical ones, because I think that if you at some point decide to get more familiar with this business, you could appreciate how become simple to look at some question from a more geometrical and combinatorial point of view, rather than having the standard approach of shut up and compute. And well, I hope that you have some questions about all this, even if I understand that you probably will need to digest it a little bit more before having some more insights and curiosities and other questions. So I can stop here.
Thank you, Paolo. Don't be shy if there are any questions, curiosities, or whatever. There is a question in the chat.
Yes, I think I read it. Yes. Okay. So as I just mentioned, we know that there are factorizations using this language. We know that there are factorizations for the wave function. There will be a missing link through the fact that these are implied by unitary, because, for example, in the case of flat space, the reason for which you know that the Cartesian rules are associated to unitarity is because you have a proof based on what is called the largest time equation. That here is a bit missing. However, I think this year, between the end of last year and this year, there have been a set of three papers published by Enrico Payer and his group in Cambridge, where they were able to connect some different sort of Cartesian rules for the ones you can get from the cosmological polytope and unitarity. And but their statement, what they call the cosmological optical theorem, really it's just a feature of perturbation theory, because in order to be able to play a similar game on what one does in amplitude, one thing that they did is consider that you have your evolution operator, so you go explicitly in the bulk. And if you do perturbation theory, that evolution operator is just the identity plus some correction. But that's true just in the case of perturbation theory. Let me let's see. So in amplitude, what you do? In amplitude, you have this matrix. You know that this matrix has to be unitary. And in principle, you could think to write an S matrix like E to some operator. However, we don't do this typically. What you do is that you write S as 1 plus IT. And then when you plug this there, you get some relation will give us the optical theorem. Okay, and then you sandwiches and you get you sandwich with states, and you get that let's say 2 times the imaginary part of the amplitude is given by an integral over some set of states for the amplitudes which depends on some in states and q, and amplitude bar which depends from out states and q. This statement do not rely on perturbation theory whatsoever. You simply wrote this guy in this way because you thought that it was convenient, and then we have an interpretation of what the amplitude this operator means. Okay. What they do instead, you take the evolution operator that typically is given in this, actually more generally is given in this form. Sorry. Okay. But they say, okay, let's consider perturbation theory, and then if you write perturbation theory, you can write this object as 1 plus some del u. And then they can play some similar games that you do in amplitude in that case. So so that's very nice. And so these are and so they get some rules, some cutting rules, which really concern differences of wave function rather than the wave function itself. So in a sense, so we know something, but still I think we have some deeper understanding missing, because at least ideally you would like to have a clue of what's the definition of unitarity, what's the implication of unitarity, without resorting to, at this level, doing perturbation theory. So I think these papers might have been on the list of references I originally gave to the organizers. So otherwise, I can provide them to you. But still, what we like to do is to have a formulation, a combinatorial understanding of this. And maybe it's already manifest, but we didn't get it yet.
I think we can stop the sharing of YouTube live streaming. So if there are other questions or curiosity, and okay, in the chat there is the list of the references that Paolo gave us. So we have put the references in the chat.